Alright guys, so what we're going to do for this lesson here is going to spend some time looking at the expected values of a discrete random variable. But before we get into that, I want to start off thinking about, well, what we've been looking at is probabilities. And when we start to think about probabilities and probabilities of experiments that happen over and over and over again, some questions that start to come to mathematicians' minds are, well, what would I expect to see if this experiment was to happen? Again, I've conducted it X amount of times already. What would I expect to see happening next? And we can look at that through an example here, that intuitive question that, well, how many times would I expect to see the number 2 on a standard die, if I rolled it 1,200 times? Well, we would expect it to occur 1/6 of the time, because in theory, number 2 happens 1 out of 6 times when I roll the dice. So there'll be 1/6 of the amount of times that I've rolled it, which in this case would be 200. But what happened? Well, we know in the real world that it's not always going to land exactly what the theory says. What happens when we start to get data sets that are a bit different, when our frequency of events occurring are different? What happens if we don't know the frequencies? What happens when we only describe the probability of each score occurring? What do we do there? So to start to answer those questions, let's go back and look at. So coming back, what we've got here is we've just got a frequency distribution histogram here. And we've got down the bottom there on our x-axis the individual scores, the scores 5, the score 10, the score 15, the score 20. And on that vertical axis, as much as it says p of x equals x, if we just think of this as a frequency distribution, it's, well, just how often has the score number 5 occurred? The score number 5 has occurred once. Score 10 is 3 times, score 15 twice, and score 20 once. What would I expect to see from this if I was to conduct this experiment? What number would I expect to get if that, 5's happened once, 10's happened 3? What would I expect to see? And when I start to think about that, I'm starting to think about, well, what would be that central number? What would be a really good estimate to describe a single number that describes what's going on in this data set here? And that starts to lead us to think about, the mean, or the measures of central tendency, the mean, the median, and the mode. Well, this is quite clearly numerical data, so I'm not really that interested in the mode. There are no outliers, so the median, not the best. The mean in this scenario would be a very good way of figuring out what would I expect to see. What is that score that tends to happen around the middle, that tends to come out, that measure of central. Well, we know that to calculate the mean, if we think to junior school, we add together all the scores, we multiply by how often those scores occur. So 5 times 1 plus 10 times 3 equals, there's 3 10s, 10, 20, 30, adding all our scores. And then finally, we divide it by, well, how many scores were there in the first place? Now, if we start to think about this fraction that we have there, I'm adding fractions together to add 1, 2, 3, 4 different terms together. They need to have a common denominator. Sorry, hang on. Let me backtrack there. So here's what I mean by that common denominator. 5 times 1 over 7 will give me 5 over 7. 10 times 3 is 30 over 7. 15 times 2 is 30 over 7. And 20 times 1, that's 20 over 7. I've just split that one big fraction into 4 smaller fractions, each with a common denominator. And I wonder if you can start to predict or see where this is leading. All right, so let's change this up now. Make this a probability distribution. On the left-hand side there, you can see my vertical axis now. It's no longer describing frequencies. It's describing the probability of scores. The score number 5, it's got a 1 in 7 chance of happening. The score number 10, a 3 in 7 chance of happening, and so on. So let's go through and do the same process. Let's figure out, how would I find a mean of this? Well, score 5 has a 1 on 7 and everything. Well, that looks very familiar. I don't know about you, but that's exactly how we described mean previously. If I could split my fraction up to 4 individual fractions, and that's funny enough, it equals the exact same value, 12.14. Just exactly like we described. Those two expressions give us the exact same answer. Oh, whoops, sorry, forgot about that. So here we have this E of capital X, the expected value of this data set is 12.14, and our expected value is just another way to say, well, what would be the mean of this data? So in short, the expected value is capital sigma, which in this case, like all times, it stands for, in mathematics here, it stands for the sum, and it's the sum of the score X times its probability of X. For a discrete random variable, let's now head over to our booklet and look at our booklet.
So the expected value, again, it's something that we would expect to occur. It's the outcome we would expect to occur within the given experiment. All right, so that would be, for argument's sake, the best example I can think of off the top of my head, it would be cricket. And if we think about Australia's best ever test batsman, Sir Donald Bradman, his batting average, or his expected value, was 99.94. Each time he would go out to play cricket and bat, we would expect him to score about 99 runs or 100 runs, probably scoring 100 runs more times than he scored 99, because that average was 99.94. It's close to the 100, right? It's just giving us an idea of what will happen. It's what we would expect to see. It's not what is going to happen. It won't be every single time. For argument's sake, in his very last ever batting innings, he scored a duck. He got 0 runs. It was nowhere near his average. But it gave us a really good idea of, each time he went out to bat, what we would expect to see. So the expected value, E of X, notice how it's written sort of like a function. It's E of capital X, but it kind of appears like a function. We're not going to talk about that in too much detail at the moment, but in a later lesson, I want to come back to that idea as well. That we can think of it, it's a function, it's something that happens. And for a population, the expected value is actually equal to the mean for a population. So let's go through and look at some notation here. So if capital X, if our variable takes on any set of scores, my first score, my second score, my third score, some other score along the set, could be the 5th, the 6th, the 22nd score, all the way up to the nth score, well, each individual score has its own probabilities that match it. And we saw that previously in the probability distribution histograms that we saw in the slide. So the expected value is just the score multiplied by its probability plus the second score multiplied by its probability plus the third score multiplied by its, and so on all the way until you get to the last score. Now we can describe that as capital sigma being the sum of all the scores, starting at the first score and going to the nth score of the individual score multiplied by its own probability. That's one way of describing it. This notation down here, it says the exact same thing. is that the expected value, or the population mean, is capital sigma, so the sum of all of the scores starting at x equals 1, all of the scores multiplied by the probability of that score happening, add all of them together until you get to the very end. So it's just summing together all of the scores timed by their, or multiplied by their probability. Okay, cool, beautiful, moving on. So let's look at this worked example here. We're giving some kind of probability distribution. Let's just double check, all our values, they're all numerical. They do add to 1. Trust me. If you don't trust me, add them. They add to 1. And all of the probabilities are greater than 0, but less than or equal to 1. So this definitely satisfies the conditions of a probability distribution. So because that satisfies probability distribution, its expected value is just the first score multiplied by its probability plus the second score multiplied by its probability plus the third score multiplied by it, the fourth score, and finally the fifth score. We multiply all those scores together and we get by their probabilities, and we get our expected value of 2.85. Now let's just take a moment and think about 2.85, that this table is the distribution of a discrete random variable, our DRV, our discrete random variable. Now, we classified something as discrete as whole numbers, something that we count up. But here we have an outcome of 2.85. That's not a whole number, right? But that would be just like me, and let's use this example here. The average number of children in a family is 2.3. No family, and we've discussed this in class, will ever have a fraction of a child, but it gives us an idea of how many children we can expect to see in a family, and that's somewhere between 2 and 3. Some families will have 2, some families will have 3. Because it's 2.3, that's actually, if we round it, it's going to be closer to 2. We would expect to see 2 more often than we would see 3, but there are going to be more 2s and 3s than anything else. When we come, that's what we expect to see. But don't get that confused with the most likely outcome, right? The expected value and the most likely outcome are two different things. The most likely outcome, it's just the one that's got the highest probability. And in this situation, the most likely outcome is the number 3. 3 kids in a family, or whatever 3 is, right? But it's not our expected value. It's not what we'd expect to see every single time, right? We just, 2.85, that's what we would expect to see majority of the time, something around 2.85. The most likely outcome, if I was to just conduct this experiment once at random, would be the number 3. All right. So hopefully there's some language and some formal definitions described for you there, particularly with that notation, that sigma notation, adding together every single score multiplied by its own probability. In the next video, we'll start to look at the worked examples through our booklet.